It's my pleasure to introduce Professor Linwei Wang. Dr. Linwei Wang is a professor of computing and information science at the Rochester Institute of Technology in Rochester. She directs RIT's signature interdisciplinary research area in personalized health technology. She also directs the computational biomedical lab that conducts interdisciplinary research at the intersection of artificial intelligence and healthcare, especially in the development of Bayesian inference and Bayesian deep learning techniques for health data understanding. Her group's research is supported by over 8 million funding from the National Science Foundation and the National Institute of Health. Dr. Wang serves as a current member on the board of the MICAI Society. She is a recipient of the NSF Career Award in 2014 and the United States Presidential Early Career Awards for Scientists and Engineering in 2019. Her speech title is Few Shot Generation of Personalized Neural Surrogates for Cardiac Stimulation. Prof. Wang, please share your screen.
Thanks very much for the introduction. Can everybody see the screen?
Yes.
Okay. So thanks very much, and thanks for the invitation. It's a great pleasure to be here today. So I thought I will just talk about one of our recent work that was presented in MICAI 2022 on what we were working on in terms of trying to speeding up the cardiac simulation models. So I think for some of the audience probably are familiar with the concept of virtual heart models, or in general just a mathematical simulation model that is able to work as virtual platform that start to recently in the last decades also start to see a lot of potentials in clinical applications, for instance in predict risks in health planning therapy. So we can plan therapies on the virtual heart instead of on the actual patient, and for facilitate with clinical trials. Despite all this promising potential, there are two critical challenges towards a sort of mass scale clinical adoption of this type of models. One of them is this type of models needs to be personalized to an individual subject. So for instance, in the heart, this includes the personalization of the anatomy of the heart, and more important, or in a more challenging way, also the tissue properties, the parameters of the mathematical model. And in current, with the past many years of research, I think personalizing the geometry has become a bit more advanced in the with the help with medical imaging and medical image analysis. But personalizing the tissue property, or basically the parameter of the mathematical model, still remains a critical challenge. And then after the model is personalized, and if we want to utilize it for predictive modeling or treatment planning for a patient, the computation of this type of mathematical models are typically very heavy, so that's another obstacle towards adoption. So there's been a lot of work to address both aspects. In terms of personalization of the model, this has been I think a topic over probably the last 20 years in MICAI, in the general MICAI community. And there's been a lot of work that's been done. This includes deterministic optimization in terms of just trying to find what is maybe the optimum parameter of a mathematical model, or of a virtual heart model that will fit the clinical measurement we have. And then this has evolved from earlier, derivative-free type of optimization to more recent years. Start to have the use of active learning or reinforcement learning type of method to be used in trying to personalize a mathematical model like this. And of course, then there's also the counterpart of trying to do this in a probabilistic manner, so that you not only get an estimate of the optimal parameter, but also get a distribution so that you have the uncertainty of the parameter, which give you additional benefits in doing, for instance, quantifying the uncertainty that's associated with the model and the simulation you have. So in general, there's still a lot of ongoing research on this. In general, the great challenge associated with this one is, if you imagine this type of virtual heart model, behind it is typically a set of very complex, let's say, partial differential equations. So the parameter of these equations is relation to what we are looking at in the clinical data. There's a very complex nonlinear relationship, and these parameters are typically very high dimensional, especially if you consider the tissue property of the heart that can be changing locally. For instance, in the heart, if there's a region of scarred injured tissue, then the parameter that we use to describe this is not only one global parameter for the entire heart, but you have to attach it to every local region of the heart. So it's a very high dimensional set of parameters to, because of this, it is typically very difficult to trying to personalize the parameters of these models. And then in all of these methods that are shown here, every time you want to optimize or to estimate the parameter of these models that will match your data, it typically involves a lot of call to these models. Just if you imagine, when we solve any optimization problem, you typically have to iteratively evaluate trying to figure out what's the value of this function you're trying to optimize given in the input space. So in this setting, this function you're trying to optimize has a very heavy model in it. So when you call it repeatedly, it becomes very expensive. At the same time, on the other hand, recently, there's been a lot of interest in trying to do surrogate modeling in the form of a neural network. So in the past, surrogate modeling itself is not a new concept. In the past, surrogate model or reduced order model is typically done by physics-based reduction of the model, reducing a very complex set of PDEs to a simpler set of PDEs with a small number of variables. And in the last couple of years, there start to emerge another line of surrogate model that's based on more on machine learning or building, especially a neural network approximation of how this mathematical model should behave. So in the field of cardiac simulations, this is the progress relatively emerging. Most of the effort that has been reported is mainly in 2D, and there's some new 3D models being developed. Outside the specific field of cardiac simulation, this notion of surrogate modeling has been a very fast development over the last several years, and I think some of the audience probably are aware of this. There are, in general, two types of networks. One is a typical data-driven networks, where if you have a lot of the output of your simulation model, then you can try to learn a neural network from those data generated by the simulation model and try to learn a sort of a neural network approximation of the simulation model itself. And then there's another line of work that is known as physics-informed neural networks, where you don't supervise neural network with the data generated from these mathematical models, but you're using usually this mathematical model, usually in terms of PDEs, to supervise your model itself. But in any of these approaches, there's two main challenges. One is most of these models, when you're trained, so if you think about the simulation model, as I mentioned earlier, in terms of personalization, the point of personalization is really about, there's different parameters associated with these mathematical models, and they tend to represent, let's say, the difference among person. So when we build a neural network approximation of these mathematical models, currently the most common way to do this is to fix these parameters in the mathematical model, and then try to learn neural network that represent this mathematical model. Then the limitation of this is obvious, because then the network you are learning is only for the mathematical model with this set of parameters. If the parameter changes, then you have to relearn again or fine tune it again. And an alternative approach will be then, okay, since I know my mathematical model changes with these parameters, and it's important because this parameter represents patient-specific properties, then what I can do is, instead of learning a neural network that's fixed for fixed parameters, I can try to learn a neural network that takes these parameters as input and then output them, and then, and then generate output accordingly. So this is a very ideal situation, but this is very difficult because that means in your training data, you have to be able to train your model for this mathematical model, given all these different simulation parameters. So to create the training data will be very expensive. Of course, it would be a very large space. And the other challenge is basically when we apply this model to clinical practice, typically, just like in this mathematical models, when we're applying it in clinical practice, we have to personalize it first, because we don't really know what should be the parameter of a person until we see the data and use some method to personalize the model to the parameter. So even if, hypothetically, even if we can train a perfect neural network that, can take any parameter for the simulation model and output perfect simulation output for it, there still will be the challenge that you still have to personalize it to given clinical observations of patient when you have the data. So basically, in summary, in our current practice, we see basically these two types of efforts. We either try to personalize the simulation model to clinical data, or we try to learn an efficient neural network approximation of this simulation model, but typically we're doing it for generic parameters. So how can we do these two things at the same time? Can we learn a neural network surrogate of the very expensive simulation model, but at the same time learn it such that it is actually personalized to an individual? And that's basically the question we're trying to answer. And our whole idea is basically built on the concept of meta learning. So the idea is just, in the practice, we are trying to, current practice of surrogate modeling is basically trying to learn one neural network for one set of one mathematical model with a fixed parameter. So, but we don't want to do that because that's, only limited to one particular setting. You can extend it to subject-specific settings. So what we want to do is not to learn a fixed neural network that's able to describe the cardiac activities for a particular parameter setting. What we want to do is this process, being able to personalize a neural network very quickly to some patient-specific data we have. And with that is our fundamental the idea of our fundamental idea of work that's like for future generative modeling to achieve this problem. So how do we do this? We first need to figure out, okay, what is the base model that we can use to describe these spatial temporal activities on the heart that we want to learn. So because we're looking at something that happening over space and time, and we want to have a neural network that is able to generate those spatial temporal activities for different situations. So basically we need a type of generative model over time. So what we are looking at is this sequential latent variable model. There are currently two typical choices for this. One choice is what we can say it as I refer to it as state estimation formulation, because the idea is basically like, I think everybody, if you are familiar with typical latent generative model, like a variational autoencoder, then you are familiar with this one piece of this sequence. Basically, we can train a latent variable model or VAE, whereby by this encoding decoding architecture, where you try to embed some data X to a latent variable Z and then ask it to reconstruct the same data. And then when we formulate it in a generative modeling format, then when this model is trained, then you can take the decoder and this decoder can generate the data for you. So one type of sequential latent variable models is just simply to extend this over time. So, if you have a sequence of data, you can learn to encode them to a sequence of latent state. So that's why it's called state estimation. You are learning the latent state, and then this latent state is what then generating the corresponding data you have over sequence. This type of data is very intuitive, and as you know, because we're learning the latent, we're trying to embed the latent state from the data, it is very good at discovering very different data. If your sequence has some heterogeneity in it, this is very good at it, and it's very good at reconstructing the whole sequence. But if you think about it, this type of model, at every time step, you basically try to, you have to try to get a estimate of what's going on of your latent state at time t from your observation, and then this is what you use to predict the next time step. So because it is trained to do this, this model will have limited ability to try to just go, if I take Z0 to ask it to do Z1, Z2, Z3, Z4 by itself, it will have trouble doing, it will have trouble to do this because it was not taught to do this. The model is taught to get an estimate from the ZK first and then predict next step. So the model is good at predicting one step ahead, but it won't be very good if you remove the encoder and just ask this orange decoder to do the whole sequence by itself, because it has a very strong reliance on this encoder at every time step. So that's what this means, that this model is very good at reconstruction, but this orange piece has trouble, will have limited ability to predict ahead without this blue encoder. So another option of the base model is this type of latent sequential model. The formulation the difference might look subtle, but it's pretty fundamental. So if you look at this type of model, what the model does is it takes an initial cups several frames to get us the latent state only at the initial latent state. And from there, this model is asked to predict all the time frame ahead by itself, and from there to predict to basically to get all the observations up to time k, but also way past time k. So k is what you're using to infer, to encode the initial latent state. So this type of model, as you can, I think, intuitively, so this is what we call system ID formulation, because the encoder you don't try to embed or try to learn the encoding of all the latent state at every time step. You only learn first step, then after that, this model itself has learned a dynamic function that is able to predict every future time frames. So it identified the system by itself. So this is what we call a system identification formulation. So this model is very strong at forecasting because that's what it's taught to do. It's trained to do this. The limitation of this type of model is that, as you can imagine, this formulation alone, when I train this on a data set, I'll be learning one set of this latent dynamic models out of it. So this theta here is the parameter of this latent dynamic model that describe how Z0 goes to Z1 goes to C2 in the latent space. So basically, when we do this, we are assuming all of the data has a latent dynamic function that can be described by the same parameter. So the fundamental problem of this type of formulation is, yes, it is very good at forecasting because it's trained to do forecasting, but it is also trained to learn one latent dynamic function at a time. It's not able, so it has this fundamental assumption that all your data that's training this model for has to be able to be described by this one model, and this one model needs to be able to be used for all the test data there. So by the time we got here, our intuition is very we thought it's very simple intuition, because this type of formulation originally learns one dynamic function at a time for the training data. So you're learning one dynamic function for the whole training data. So what we thought is basically, instead of learning that one dynamic function at a time, we can just use meta learning to try to learn how to adapt this dynamic function to few short examples. So that's a very simple, I think that's basically a very simple formulation intuition on our side. So the idea is, instead of learning one dynamic function at a time from the entire training data, the idea is that, if we have data set with data that coming from dynamics that are similar but are different, for instance, because the parameter of the dynamics are a little different, of the governing dynamics is a little different, then we can treat these different dynamics as this different task in meta learning. And what we can do is to come up with a strategy that every time, if you give me a couple of examples, I can learn to adapt these latent dynamic functions to these examples and give you a a specific dynamic function that's personalized, that's adapted to these examples. And that's the idea of our few shot neural surrogate framework. And then it basically has these two components. One is this latent function. So in existing work, this will be a fixed function. So here we just simply ask this function to be conditioned on some knowledge. And this knowledge is the knowledge about the specific dynamics. And how do we get this knowledge? This knowledge is obtained by a meta model. And this is in the meta model in the form of a feed-forward model, feed-forward embedding, set embedding. So basically give me a set of few short time series. I can learn to embed or extract knowledge from it that's specific to this dynamics. And from there, I can quickly give you a dynamic function that's unique to this set of examples. And this is basically the fundamental, that's the general formulation of what we are proposing. And we are, on one hand, we're evaluating or developing this for a lot of general benchmark data set outside medical imaging. But for MICA 2022, we also developed this for this cardiac simulation. So imagine that what we want to develop is a neural network that is able to mimic what a simulation model will do. And what this model need to do in terms of cardiac, electrophysiology to simulate the electrical activity of the heart, what this model need to be able to do mainly is that give me some initial location of electrical activation. I will be able to generate for you the electrical activation sequence throughout space and time as a result of a set of PDEs. So we want this neural network to be able to do that. But we know that this type of activation sequence is unique to each person, depends on the parameter of the underlying PDE. So that's why, instead of fixing the parameter of the PDE and learn one model, one neural network counterpart out of it, what we want to do is to be able to, let's say, given a set of PDEs, their parameters are all different, and they have the corresponding, simulation outcome of it. What we want to be able to achieve is to use meta learning to be able to achieve that at any time, if you give me, a very small number of examples that's corresponding to the simulation coming out of one PDE parameter settings, I will be able to generate or adapt a neural network that has the dynamic that's corresponding to that PDE. So that's how this looks like. So basically what we want to do is basically to be able to have a general model that is given any initial location of activation, and then give a set of, so the Y here is the example, the data from context set. So context set means it is not the query example we are trying to forecasting on, but it's coming from a set of context samples we know that's coming from the same heart, but it's not a sequence we're trying to test on. And then given that, we basically need to learn a model that's able to maximize this likelihood. And this likelihood in this equation, it has two main components. One is you need this first P here is the general model, the decoder you need, and then the second Q here is basically the embedding, the set embedding from the context set. So there's two components, as I mentioned. So the first component is the decoder. So this decoder needs to be able to do two things. One is we need this latent dynamic function that is able to basically go from latent state t to t plus 1, so to predict ahead. And like I mentioned, we don't want this to be one fixed function learned from the data, learned for the one set of data. We want this function to we want to be able to change it according to the context set, to a small set of few short examples. So in our formula, this function takes z0, and the z0 is encoded from the known location of the activation. And then this model is conditioned on some few short embedding. And then, of course, after you have the latent dynamics that describe dynamics over time, then you need to have an emission model that takes this latent state z and generate it to the data space. And this we realize with a graph convolution network. And now the next question is, okay, once we have this decoder, so after this decoder is trained, we should be able to just take this set of decoder. So this decoder has dynamic part and it has the emission part. And then this decoder, once we train, this is what we use as the subject specific neural surrogate. It is neural network that's able to emulate what is the cardiac simulation will produce on this heart. So the only thing we need to know is, the way we obtain a patient-specific neural surrogate is by obtaining this condition z of c here that's coming from the few shot. So the next question is basically, how do we get this conditional embedding? And this full embeddings, this is, as I mentioned, this is basically the meta model we have in the formulation. So the meta model basically is an encoding network, and it is based on set embedding. It's based on the assumption that, a set of data will share the same parameters. So basically, if you have some prior observations from this person, then all of this data should be corresponding to one embedding, and that what you can use to obtain the personalized surrogate model. So this is a feed-forward model that basically take a set embedding. The set embedding is basically achieved by embed individual context examples and then aggregate them in the latent space and get a set embedding. And then once we have this, everything can be solved under the variational inference framework. So that's basically coming back. This is basically what we have. And the way this model is trained in a meta-learning setting is basically, it's in an episodic setting. We have a large set of meta training set. And in each episode, there's context set, and then there's target set. So this model is asked that at every episode, if I take the context set, get embedding ZC, and then use this ZC for each query example, given the initial activation location, I need to be able to produce the whole spatial temporal signals of my simulation. In here is the electrical activation. So, this coming from context set, and the rest is for the query set, which are individual time sequence that are different, but it's coming from the same dynamics. So we did this in sorry for that. So our synthetic experiment is done on a large set of cardiac simulations with 16 different parameter settings. So that representing 16 different dynamics. And then for each parameter setting, we simulated electrical activation corresponding to 200 different locations of activation. And then to compare with this model, we consider two types of baselines. One is use the actual simulation model and then try to personalize it with probabilistic techniques. And in particular, we use this Bayesian optimization technique. This is something my group has done in the past. And then we also considered another neural surrogate that's everything else looks exactly the same like this model. The only thing is this branch that's supposed to be able to get some patient-specific parameters for the neural network. This is not done on a meta set. This is done just so no meta learning, basically the same network, but this branch is coming from the same, using the same time sequence of a person trying to learn to be able to personalize the parameter. So this is what we call the instant specific embedding. So this is some examples of what we do on the meta test set, 2 cases over time, and you can compare these different rows of, this meta PNS is our presented model, and this is the same neural network, but if you do it on instant, like you try to get a patient-specific embedding on each instance instead of trying to use map learning. And then this is the 2 method that's used optimization on the simulation model itself. And then you have the results here in terms of the quantitative results. So the quantitative result shows that the meta learning work is very strong in terms of performance. And then we also tried, some of you may be asking, how large is this context set you need? So we actually need a very small number of examples. So we've tried few shot of, K shot K from 1 to 5. And you can see that other than K equal to 1, that caused some difference in performance. Otherwise, the K doesn't really cause much difference in performance, and K can be changing as well, both in training and testing. And we've also tested this in a real data experiment. So this is with collaboration with our collaborators in University of Utah. That's a tank model where there's a beating heart of the animal that's emerged into a fossil tank. And then with this, we can measure the electrical activation both on the hearts and on the body surface at the same time. And then we can use that to test if we can quickly use a small number of measurements on the body surface to personalize a neural network that's actually then you can use to predict the electrical activation on it. And what we did is, we did not retrain the model. The model we had was still trained on the simulation data, and we just directly apply on this. And every time we're trying to use 4 of the pacing size data as the context set, and use the one leaved out for the query to test. And then this is some examples of, and this is the result we get from both quantitative and then some examples of how on the test set, the prediction from neural network looks like compared to the actual measurement. So if you look at quantitatively, there's a notable drop of performance from the simulation result, but we're quite happy from this because the model was not retrained at all. The model was trained on the simulation data and directly applied here. So that generalization is very large gap considering shift between training and simulation and real data. So in conclusion, we are trying to show that there's a way with meta learning we can try to learn to personalize a neural network surrogate for actual cardiac simulations using only a very small number of context example for a person. And this is a proof of concept. There's a lot of work to be continued, including trying to test this on higher fidelity simulations, trying to, right now, the context data for personalization is the body surface ECG recordings. We are trying to pursue using a, different modality data, and also to try to generalize to more complex real data applications. Okay, with this, I want to thank the students that are leading this work, and also our collaborators in University of Utah and Rob and his group, and our the fundings that's supporting this work. Okay, so I will stop here now, and if there's any questions, I'd be happy to take it.
Thank you, Professor Wang. Thank you so much for your excellent speech. Is somebody have any questions about Professor Wang? If you have any questions, please feel free to ask.